Okay, so so welcome to the start of the second day. Our first speaker is Mrinal Kumar, who will tell us about polynomial factorization.
Thanks, Srikanth. I'm audible? Okay, good. So I feel that there's an obligation to thank the organizers of this workshop, and feel an inherent reluctance to do this with a straight face, because my talk was scheduled for tomorrow and got pre-scheduled, preponed for today. So I thank 2/3 of the organizers for inviting me, and
the blame goes to Prahladh.
The other thing is that I hope at the end of the talk there's something that you learn from this talk that's useful in life. But just to make sure that you actually learn which is useful in, something that's useful in life. So I learned something that's useful in life in the last couple of days. When you are getting off a flight and the attendants tell you to check the seat pockets, you should check the seat pockets. I left the notes for this talk in my flight. So yes, next time. All right, so the plan is to prove this theorem. It's a well-known theorem. It was proven by Kaltofen in the 80s. In fact, he proved something much stronger than this. So this theorem just says that if you have a polynomial which has a small circuit, then all its factors also have small circuits. And by small, I mean something which is polynomial in the size of the circuit, the number of variables, and the degree of the original polynomial. And what Kaltofen also showed that there's an efficient randomized algorithm which will output the circuits for the factors. We will not talk about algorithms for this. I'll just talk about the closure result for arithmetic circuits. The statement itself is a bit surprising because we don't know such statements for almost any other model of computation that you can think of. So formulas, branching programs, constant depth circuits, we don't know if the complexity of the factors is polynomially related to the complexity of the original polynomial. So it's quite surprising that this is true. I also think this is one of the more sort of underappreciated statements in complexity. We don't quite acknowledge how neat a theorem this is. And there have been many proofs of this. So Kaltofen's original proof is of course there. There was a proof by Bergieser in early 2000s, which is considerably simpler than Kaltofen's argument. There have been other arguments. So Nitin, Prajal, and Amit have a proof. Raphael had a proof in one of his papers, and so on. So I'm going to talk about another proof. This came up in the course of some conversations with Chi-Ning Chow, who's here, and Noam Solomon. And the plan is to show you almost all the details in the next 1 hour, 1.5 hours or something. So stop me and ask questions if something comes up. All right. So for the first 5 minutes, I'll basically do some pre-processing. We'll reduce it to a problem which we'll then solve in the next hour or 40 minutes or so. So the first thing to note is that to prove this theorem, theorem 1, for irreducible factors. Right? We could upper bound the complexity of all the irreducible factors by polynomial in SND. The complexity of the factors we upper bounded by. So in particular, the following situation happens. So there are two cases to consider. So it must be the case that either f factorizes as g times h, where the GCD of g and h is 1. So either this or f is a power of g. I just want to prove this theorem. I want to prove an upper bound on the circuit complexity of g. Yes. Okay, so either it's the case that f is equal to g times h for some h such that the GCD of g and h is 1, or f is a pure power of g. Okay. Now, most of this talk will be about this case, and let me quickly show that if we have a solution to this then this also follows immediately. So the key is to look at the polynomial, let's call it Q, which is z to the e minus g to the e, or rather z to the e minus f. So this is equal to z to the e minus g to the e. And this factorizes as z minus g times z to the d minus 1 plus this is fine. So I'm not, the proof of this fact will not use the fact that g is irreducible. It will just use the fact. So you can just take this to be the power of your irreducible. Okay, so if this is the case, if f is a pure power of g, let's look at the polynomial q, which is z to the e minus f. So this is z to the e minus g to the e. So this factorizes in some way, and z minus g is a factor of this. And the GCD of this factor and this factor is 1. Note that if we upper bound the complexity of this factor, z minus g, we upper bound the complexity of g. Okay. So without loss of generality, we can just focus on this case, and this will imply the theorem in general. Okay? Are we good? All right. Okay, so we'll just, sorry? No, it doesn't. I'm not going to give you an algorithm. I'm just going to give you an upper bound. As long as there is some e, this is fine. All right, so this is what we are going to look at. Let's just clean up the question here and put it in a form which then becomes easier to analyze. So the first case to consider is that g and h have a common variable. Or rather, let's do. So if g and h do not have a common variable, then note that the circuit complexity of g is upper bounded by the circuit complexity of f. You can just set the variables in h to some random values so that h is non-zero, and then that gives you a circuit for g. So this is again easy. Interesting case is when g and h have a common variable. So let's just set some notation. So the set of variables we'll have are now x and y is the common variable. So we have f of xy is equal to g of xy Yeah, so we'll talk about fields of characteristic 0 or something. Right, so yes, so no positive characteristics. So everything is characteristic 0. Yeah. No, we don't. No, we don't, but there is some e, and as long as there's some e, this is fine. All right, so this is the case we are considering. Okay, so what I'm going to do now is I'm going to do an invertible linear transformation on the basis so that all these guys become monic in y. Okay, so we want to make everything monic in y. So one way of doing that is I'm going to substitute xi by xi plus alpha I times y. For all I, we are going to do this where alpha I is our random field elements. Okay? So the claim is that with high probability, after this transformation, so let's say that f gets mapped to f tilde, f hat, g gets mapped to g hat, h gets mapped to h hat. So without loss of reality, we'll assume that f hat, g hat, and h hat are monic in y. Okay, so once you do this random random invertible transformation of this type, what will happen is that if the degree of f is d, then the degree of f in y will become d with very high probability. And the leading coefficient will be a field element, a non-zero field element. So let's just divide everything by this non-zero field element everywhere. So everything is monic. If I write here, is this visible? All right, so let's write f of xy. Okay, so now we are going to view the whole problem as a univariate problem in y. So think of all of f hat, g hat, and h hats as coming from here. So these are univariate polynomials y, come from the ring of polynomials in the x variant. I'm going to drop the hats because it's a pain, right? Okay, so f is monic, g is monic, h is monic. So f is of the form y to the d plus x sub d minus 1 where each fi is polynomial in the x variables. Okay, and similarly, let's also write g and h as monic polynomials in y. So g of xy this is y to the k and let's say the degree of h is r. So this is y to the r so each gi, each hi is a polynomial. Okay, and the thing is, since f equals g times h, k plus r is equal to d. Okay, so what we know is that f has a small circuit. What we would like to show is that g has a small circuit, h has a small circuit. So note that it suffices to show that each of the GIs has a small circuit and each of the HIs has a small circuit. Each of the GIs and HIs has a small circuit. You take those circuits and you add them up with appropriate y weights to get a circuit for G. The other thing to note is that since F has a small circuit, you can interpolate with respect to y to show that each of the FIs has a small circuit. So there's a factor D blow up in the circuit size in the problem. So let's just note this as observations. So Fi for all I okay, and based on what we said right now, we'll just try to show that each of the GIs and each of the HIs has a small circuit of size polynomial in S, D, and N. Okay, so the way we are going to do this is we are going to look at this identity that G and H satisfy. So one remark was that we started with the case that G and H have GCD1. We did some invertible transformations in the process, so this will maintain the GCD. The GCD of these translated versions will also. So let's view this identity and let's plug in this way of writing F, G, and H. So this is y to the D plus D minus 1. So this is an identity in Y. View this as a univariate. There's a univariate polynomial on the left in Y, there's a univariate polynomial on the right, and they're equal. So if they're equal, if these two polynomials are the same, this implies some relations between the coefficients of various things in Y. So the coefficient of Y to the D on both sides is 1. Right, so the coefficient of Y to the D is 1, K plus R is D, coefficient of Y to the D is 1. So this is fine. So what happens to the coefficient of Y to the D minus 1? On the left hand side, this is F sub D minus 1. On the right hand side, this is 1 times HR minus 1 plus 1 times GK minus 1. So let's look at a few more things. So Y to the D minus 2. This is F sub D minus 2. HR minus 2. And so on. So if you look at the last few terms, if you look at the coefficient of Y, this is F1 here, and this is going to be H0 times G1 plus G0 times H1. Right, so these identities must hold for F equals G times H. Okay, so note that if you view these as polynomials in the HIs and GIs, these are degree 2 polynomial identities in HIs and GIs. So let's define, okay, so we'll define a bunch of, we'll define a system of quadratic equations, and HIs and GIs will be solutions to that system of quadratic equations. And our goal is to show that these HIs and GIs have small circuits. And the way we'll show that would be, we'll look at the system of quadratic equations, and we'll show that, basically, somewhat constructively, we'll show that any solution to the system of quadratic equations will have a small circuit. So let me say this properly. So U0, U1 up to UK minus 1 to VR minus 1. And let's define E0 to be F0 minus U0 V0. E1 to be F1 minus U0 V1 minus U0 V1. So on, and E sub D minus 2 to be D minus 1 to be VR minus 1 plus UK minus 1. Okay, so we have K plus R variables, and we have D equations, and K plus R is equal to D. So this is the right number. Okay? And the observation is that GK minus 1, GK minus 2, so on. G1, G0, HR minus 1, HR minus 2, H1, 0. Is the 0 of the system E1 equals 0, E2 equals 0. Okay, so we should do this as a polynomial system here. So the coefficients are coming from the ring of polynomials in the x variables, and then you have the u and the v, which are the original variables. Yeah, I did. Thanks. Okay. So far, so good. Yeah. That's correct. Yeah. So we'll try to isolate a solution in some sense. And okay. So are we good so far? So let's observe a few things about EIs. So the first observation is that each EI has a circuit of size order s times t. Right? Because a circuit for EI is just some circuit for Fj for some j, or Fi, and then a bunch of a quadratic polynomial in the U's and Vi. Maybe we should add some d square term here. All right. So this is an interpolation trick. So you view f as a univariate polynomial in Y, and Fi's are the coefficients of this univariate polynomial. So just evaluate this polynomial for a bunch of values of Y and just interpolate and find the coefficient. Okay, so very good. So EIs are what we are going to look at, and what we'll use is this particular condition. Questions in the setting? Okay. Yeah. Yes, that's correct. You know F, so you know Fi's by interpolation, by exactly. You take the circuit for F, evaluate it for a bunch of values of Y, and just take their linear combination. So we know circuits for F, each of the Fi's, and so we circuits for the EIs. All right. So the way we are going to the way we want to proceed is we'll look at the system of polynomial equations, and we'll basically try to construct these GIs and HIs as solutions to the system iteratively. So it's a bit hard, so I don't know what's the right way of saying this. Let me write a lemma and then that makes things clear. Okay, so the lemma says the following. So let A0, A1, So hypothesis of the lemma is that we have a bunch of polynomials which agree with i's and the h's up to monomials of degree at most L. So if you look at the monomials of degree at most L minus 1, the lowest degree monomials, you see exactly the gi's and the hi's. Okay, so this, and there's a circuit, let's say C sub L, which computes A0 up to AK minus 1 and B0 up to B R minus 1. So there's a multi-output circuit computing a bunch of polynomials, and these polynomials agree with the GIs and the HIs up to lower degree monomials. That's the hypothesis of the lemma. So then, there's a circuit C sub L plus 1 which computes A0 hat, A1 hat, AK minus 1 hat, B0 hat, BR minus 1 hat, such that AJ1 hat is equal to GJ1. Okay, so our hypothesis was that we have a bunch of polynomials. We have somehow managed to get our hands on the lower degree homogeneous components of the GIs and the HIs. And this lemma says that one can get our hands on homogeneous components of one higher degree of the GIs and HIs. And moreover, so the size of C sub L minus L plus 1 is at most the size of C sub L plus some S and D. So some polynomial, some fixed polynomial blow up, some additive polynomial blow up in the size of CL if you want to compute the circuit C plus 1. Okay? These are polynomials. They're going to be polynomials. So it's true for all L, right? Yeah, so I didn't want to, so to be completely right, accurate, I have had an L in all the indices, but I'm not avoiding it. BR minus 1, yeah, that's right. Okay, so what this lemma is basically saying is that if you can somehow get your hands on the homogeneous components of the GIs and HIs of degree at most L minus 1, then there is a way of getting our hands on the homogeneous components of GIs and HIs of degree at most L. And in the process, we do incur a blow up in size of the circuit computing these guys, but the blow up is native and not very large. It's some fixed polynomial blow up additively in the process. We can do this for all L. Okay. So let's first observe that this gives our theorem. This gives what we wanted to prove, and then in the rest of the time we'll try to prove this. Okay. So do you see why this gives the theorem? So note that GIs and HIs, these are polynomial in X variables. So in particular, their degree 0 homogeneous component is a field constant. So it has a small circuit. So now invoke this lemma, and this will tell you that there is a polynomial which agrees with the GIs and HIs up to degree 1, which has a circuit of size S and D to the 100, maybe 2 times that. So now you have gotten your hands on the degree 1 homogeneous component. So then we'll apply this lemma again for L equals 2, and we'll proceed as follows. So in every step, we are additively increasing the size by something like S and D to the 100. And we'll do this for D iterations. The end of D iterations, we'll have a circuit C sub D, is a multi-output circuit, computes a bunch of polynomials, and these polynomials agree with the GIs and the HIs on homogeneous components of degree at most D. And the degree of F was at most D, so the degree of the GIs and HIs is up bounded by D. So now we have a multi-output circuit of size D times S and D to the 100, which computes the outputs are basically GIs and HIs plus some higher degree homogeneous components. So we'll again apply this homogenization trick or interpolation or one of these things. So that incurs another polynomial factor blow up in the size, and we'll have a circuit which computes the GIs and HIs. Yeah. Do we know what? Do we know degree? No. No, you don't need it. If you are just interested in lower degree homogeneous components, yeah, you don't need to. The blow up, the price that you pay in homogenization is polynomial in the maximum degree homogeneous component interested in, even though the degree of the circuit could be much larger. Okay, so the point is that once we have this lemma, we'll start from the base case that the constant terms of GIs and HIs trivially have a small circuit, apply this lemma D times, end up with a multi-output circuit which computes some polynomials, but we know that these polynomials agree with the GIs and HIs on the lower degree homogeneous components. So then there is some homogenization that has to happen on top, and that will give us a circuit for GIs and HIs. Once we have circuits for GIs and HIs, we can get the circuit for G and H by taking appropriate Y-weighted combinations of them. Questions? Yeah. Yeah, so, right. So at some point I'm going to do a random linear transformation to make sure that this happens. So this lemma just says that, this lemma requires a non-degeneracy condition which I'm not mentioning right now. Now his question was, there should be so his question was, the way we are trying to use this lemma was that in the base case, what if there are two solutions to that system of equations which agree on the constant term? How do you get your hands on both of them? That's what you're asking. Right? So we'll make sure that that doesn't happen. Yeah. So it's important that this blow up is additive. I cannot write even a factor 2 here, otherwise I'm going to do this D times, so 2 to the D is too large a price to pay. So it's important that the blow up is additive, and this really uses the fact that it's a multi-output circuit. I can reuse computation quite a bit. I don't know how to prove this for, say, branching programs. All right, so are we good so far? So the only thing needed to prove is this lemma, and so there's something that I'm hiding here, so this is not completely correct as it is, but morally correct. Okay, questions so far? Yeah. Louder. Yeah, I mean, everything we have done is for generic polynomials, right? We did not use any model of computation so far. We just used the fact that you can do interpolation, which you can do for practically any self-respecting model. Right, we also did this affine transformation somewhere, right? We did this linear change of basis. So you can't work with sparsity, for instance. So I have 10 minutes right now. So can we go on for a little longer, just finish it and be done? Is that fine? Okay, so for the rest of the time, we'll just try to prove this lemma and try to address Srikanth's question about it. Okay, so this lemma doesn't mention EI somewhere, but I defined EIs, so EI should come into picture somewhere in the proof. let's start with some easy observations. So the first observation is that, so we already observed that G comma H is a common zero of E0 up to E sub D minus 1. So A and B are what are there from the hypothesis. So observe that each of the EIs, if you plug in A and B here, so this is going to be 0 mod x to the L. So since G and H is a solution to the system of equations, G comma H is identically 0. So now you just look at this identity and go mod x to the L. And if you go mod x to the L, you know that of the AIs and the BIs agree with G and H, so you get that. Okay. So this was the first observation. So what we'll try to do is, okay, so now, so basically we have homogeneous components of degree at most L minus 1 of the G and of the GIs and the HIs, and we want homogeneous components of degree L, degree up to L. We already have homogeneous components up to degree L minus 1, so the only thing we really care about fixing in the proof of the lemma is homogeneous components of degree equal to L. Is that right? So that's the only part of the A's and the BI's that I really like to change. Otherwise, it agrees with the GIs and HIs. So let's say so P0, P1 to Pk minus 1 and Q0, Q1, Qk minus 1, Qr minus 1. So these are homogeneous polynomials of degree equal to L, such that so Aj1 plus Pj1, this equals Gj1. So what we'll try to do is we'll try to find homogeneous polynomials of degree equal to L such that we get what we want. So we'll add these guys to the AIs and the BIs we already had so that this identity holds. So in the language of this is going to be my Aj1 hat. This is going to be my okay, so we want. Alright, so in some sense, what we're going to try and do now is we are going to use these identities, these EIs, which the G and H satisfy, to basically find PIs and QIs which satisfy this condition. And so I stated this here. So I said EI of A comma B is x to the L. And note that by the same argument, it's also true that EI of A plus P comma B plus Q is congruent to 0, must be congruent to 0 mod x to the L plus 1. So if we are able to find PIs and QIs such that these identities hold, then it must be the case that this is also true. It's for the same reason that this is true. We are just looking at the identity EI of G comma H equals 0 and we are going mod x to the L plus 1. Okay, so this is what we are going to work with. Alright, so I'm overloading notation, but the point is that think of PIs and QIs as formal variables which are going to be homogeneous polynomials of degree equal to L, such that these conditions will hold. Okay, so let's look at EI of a plus p comma p and q must satisfy this condition. So I'm going to rewrite this condition slightly differently. Yeah, I might have to erase something and don't want to erase anything. Okay, so I'm going to erase the hypothesis. I'm hoping that you remember the hypothesis. All right, so what we are going to do is we are going to look at that identity a bit more carefully, but let's digress a bit and talk about the simplification that we are going to do there in general. So what we are going to apply is Taylor's expansion. Very soon this is going to be notationally very hairy. It's already bad. So let's fix some notation here. So basically what we are going to do is we are going to look at a polynomial of this form. And I'm going to think of this as a polynomial, so I'm going to do a Taylor expansion of this polynomial around the point x, where we are perturbing everything by y. So this is equal to e of x plus sum over I yi and so on. This is familiar to everyone? This is, okay. Okay, so this is what I want to do there. And so I'm going to do a Taylor expansion where this is the edit, and this is the point around which I want to do my Taylor expansion. So this is equal to ei of ab plus sum over I okay, so what are the alphabets we haven't used? So we used A, B, G, H. We had U and V available to us, right? They're not on the board. So let's do that. So this is equal to EI of AB plus sum over I times pi. Sum over what? Yeah, so I have to do, oh, right, okay. All right, so I'll have two J's. Right, so I don't want to get the second. Okay, but note what's happening here. So is this clear? This is just that Taylor expansion done to this polynomial around this point, around the point a comma b. These are the linear terms. These are first derivatives. And I'm just separating out the q and the p part, but we don't need to do that. So these are the linear terms. Then there are going to be second order terms. So these are terms where we are going to take second derivatives of ei with respect to the bunch of variables we had and substitute a comma b for all these things. And then they are going to be multiplied by terms like pj1 times pj1 prime and things like that. So there are some higher order terms. So higher terms in p comma q. Okay. So this is just expanding this polynomial around this point. And now we only care to look at this expansion mod x to the L plus 1. Right, so now I claim that we can just drop the second order terms which I don't want to write. Note PIs and QIs are going to be homogeneous polynomials of degree L, which means that each of these terms will have degree at least 2L because there's a PI P square term sitting around each of the terms. So if you go mod x to the L, this is going to vanish. Sorry? Yeah. Okay, so if I want to look mod x to the L plus 1, so I want this to be congruent to 0. Right, so we want homogeneous polynomials PIs and QIs such that basically this equality holds. Okay. Okay. Now the point to note is that this is a linear constraint in the PIs and the QIs. And each of the EIs is going to, for every I, we are going to get such a linear constraint in P and Q. What I want to claim is we can basically solve this system of linear equation to get our hands on the P and Q. Okay. We'll also argue, so note that this is a non-homogeneous system, so it's not clear that it has a solution. But it has a solution because we know that G and H were solutions to the original problem. So this system has a solution. In fact, we'll argue that this system has a unique solution. It means that any solution we get from it must agree with the GIs and HIs. So this will answer Srikanth's question. But this proof of uniqueness will require us to do some initial random translation of the coordinate system. But is this clear? So we are going to look at this. We are basically going to look at this, this equality for every I. Each of these equalities is going to give us a linear constraint in the PIs and QIs, and we are just going to solve this linear system. Okay, so what remains to do? So what we have is a linear system of equations P comma Q. So we know that the system has a solution. Since G comma H was a solution to the initial system of equations we started with, what we'll try to do now is to show that the system has a unique solution. Okay, so once we guarantee uniqueness, we know that we are recovering the right solutions that we want to recover. And then we'll argue that you can actually recover PIs and QIs by just paying a small additional cost in the circuit size in the process. Okay, this will take us another 20 minutes, I think. So let's take a break. Yeah, if you have questions, yeah, ask me. You should have questions because I messed up the notation at quite a few places. So you don't know, so if you don't have uniqueness, you know that what you would get would be some PIs and QIs which will guarantee this condition. But you don't know that it will satisfy this condition.
What were you saying about it's not a homogeneous equation?
That system of linear equations is not homogeneous in P and Q. There's a EI term which is outside. It's of the form A times whatever y equals V, and V is non-zero. And non-homogeneous systems will typically not have any solutions. So a homogeneous system always has a solution, right? The all zeros is always a solution, but a non-homogeneous system will mostly not have a solution. So it needs an argument that there is a solution. Chandan, you were saying something?
Just the statement has some similarity with
Right. It's basically Newton iteration is what I think of it, and this is sort of a multivariate version of it, and Hensel lifting is of something of very similar flavor.
Because there, I don't see it immediately, because there it talks about
Factors.
factors and
Right.
relative factors. So I'm curious whether it can, whereas here you get
Right, I am not sure about that, but there is similarity for sure. But what is the exact formalism for this? I'm not. Yeah. Oh, I'll come to that. It's not. There is an issue somewhere. Yeah, but this lemma, everything we are doing right now is. It's in the whole argument. There's something non-constructive.